Hello everyone, I'm Bohan Zhao, a PhD candidate at Tsinghua University. And today I will give a presentation on my paper titled Enabling In-Network Computation in Remote Procedural Calls. In this paper, we propose NetRPC, a general INC-enabled RPC system to overcome the programming difficulty of INC. And our experiment results show that NetRPC can reduce the lines of code of INC applications by up to 97% with little performance loss. And as the development of programmable switches, users can execute customized programs on the switch and store the stateful states on the switch memory for computation. INC has brought many advantages to today's system designs. For example, the server function of loading, line rate computation, and network stack simplification. And up to now, INC has been widely used in many scenarios like synchronous and asynchronous aggregation, key value cache, and agreement. The first reason to use the INC is to save throughput for all reduced tasks. Here is an example of distributed training, where workers send out the gradients and accumulate on the parameter server. And in this case, the parameter server will suffer from the incast problem because all workers should send one piece of data to the parameter server. And instead, if the switch can compute the gradients instead, the parameter server will only receive one piece of data and thus can get rid of the incast problem and achieve higher training throughput. The second reason to use INC is to reduce the delay of function calls. In the case of distributed agreement, participants send out their tickets to the leader for counting votes. And instead, if the switch can work as a leader and replies to participants directly, then the delay of the voting can be significantly reduced. And although INC has brought so many advantages, the development of INC applications still faces several challenges. The first challenge is tedious network programming because users have to handle the network details as part of the INC applications. The second challenge is the complex chip-specific language. Users have to learn languages like P4 and NPL and to understand the low-level chip-specific architecture and the design limitations. The third challenge is the static switch memory layout. Since the tables and registers of switches has to be arranged at boot time, users have to reset the switch program if they want to start or remove an INC application. And here is an example compared P4 programming with the traditional software. If you want to implement a simple if-else logic on the parameter server, you can see it's quite easy. However, if you want to implement the same logic on the P4 switch, it's much more complex on P4 code. And this is because P4 language is network-centric and mainly focused on the communication. However, most of the INC users only take care of the computation for INC. And thus, we need a programming model to include INC functions. And RPC adapts INC functions better than other programming models because users only need to invoke remote procedural calls. Remote procedural calls, and there is no need to take care of the communication details. However, including INC functions in the RPC program model is not easy for several challenges in both layers. In the RPC layer, we have to provide INC functions interfaces, support concurrent applications, provide high-level data types, and organize RPC messages. And in the socket layer, we have to provide reliable computation and transmission, provide switch memory management, and flow control. In this talk, we will discuss parts of these key challenges and leave details of others in the paper. First and most important, we need to provide user-friendly interfaces for INC functions. And we found that although switch program is complex, the high-level INC primitives can be simple. And we identified 5 types of INC primitives to cover most types of existing INC applications. Here is a figure to show these primitives. In fact, these strips reflect the interaction between the data stream and the switch memory. In NetRPC, we regard the data stream as a series of key values pairs and organize the switch memory as a virtual map. And for example, the add2 on the map adds a value from the data stream into the switch memory. And the count-forward primitive can record the number of streams from different clients and forward computation results in a preset condition. And here is an example of NetRPC programming. First, we need to define the service and the messages by protobuf and import INC-enabled data types to specify which data to be processed on the switch. And we also need to specify the name of the net filter to tell the compiler where to find the description of INC primitives. The net filter is a JSON file to provide parameters for the systems. For example, the precision field tells the system the quantization factor of the INC, and the following class names tell the system where to find the data and organize the messages. And after that, we can generate the interface code automatically by the gRPC compiler. And the users only need to invoke remote procedural calls to derive INC benefits without any extra modification to code. And to support concurrent INC applications on the same switch, we implement all the strips on the same pipeline of the top node switch to support multiple applications concurrently. Here is an example of gradient accumulation in distributed training. Clients send out their gradients to the switch and invoke the add2 on the map to accumulate gradients on the switch memory, and invoke gets on the map to read out computation results into the stream. And the count-forward primitive will count the number of clients that have sent out gradients. If all clients have sent out their gradients, the count-forward primitive will allow the switch to forward computation results to the gRPC server. The RPC server will back up the computation results and invoke clear on the map to release and reuse the switch memory. And since RPC calls should always succeed eventually, so the RPC RIPs should be the same. And thus, the RPC primitives requires idempotence in addition, because we should eliminate the repetitive accumulation on the switch to cause the incorrect computation results. And thus, we need to detect resend packets with limited switch memory. In NetRPC, we assign a flip bit to each packet, and this flip bit changes periodically for every sending window. And the switch maintains a window of states and compare them with the packet's flip bit. If the packet has a different flip bit with the switch record, then it should be a new arriving packet and should be processed by the INC functions. And otherwise, if the packet has the same flip bit with the switch state, then it should be a resend packet and should be ignored by the switch. And moreover, we need a fallback mechanism because INC can fail for some reasons like insufficient switch memory. In many cases, the switch can work as the server directly and reply to clients. However, in these cases, if the INC fails on the switch, then the switch can migrate the data from itself to the server, and the server can complete computation instead. For fallback mechanism, we implement all these RIPs on the host so that the server can work instead of the switch, and users have no sense of the INC failures, and the RPC calls can always succeed eventually. And besides the user-friendly interfaces, we also hope INC can work and derive benefits. And as we know, the INC benefits mainly comes from a sufficient switch computation resource. And thus, we need a management mechanism to utilize the switch memory efficiently. In NetRPC, we address switch memory in a key value level with the assistance of hosts. In this example, when processing value streams, we assign an increasing number to each value as a key and utilize the switch memory in a pool-based manner. That is, we can release and reuse the switch memory for each sending window. And when processing key value streams, we utilize the switch memory as a cache. The values are forwarded and computed on the switch if their keys hit the key set on the cache. And the values is forwarded to the server otherwise. And since NetRPC relies on hosts to manage switch memory correctly, memory leak can happen when the client crashes and loses these states. Therefore, we need a timeout mechanism to recycle the valuable switch memory for reusage. And in NetRPC, we utilize a controller to monitor the switch for activity of applications. And applications will store their computation results on the switch. And for the phase 1 timeout, we migrate these states from the switch to the server. And for phase 2 timeout, we clear these states from the server and make up space for the new incoming applications. And this two-phase timeout mechanism balance the utility and availability of INC. And in the evaluation part of NetRPC, we use 8 GPU servers connected to 2 programmable switches. And we run 4 types of INC applications on the NetRPC-based systems and try to answer 4 questions about NetRPC's programming simplification, system performance, concurrency, and reliability. First, we compare the lines of code of NetRPC-based systems with the prior arts. And we can find that NetRPC can reduce the lines of code of applications by up to 97% for different types of INC applications. And we also measure the basic performance of NetRPC-based applications compared with prior arts. And we observe that NetRPC achieves similar performance to baselines even after the programming simplification. And moreover, we measure the end-to-end performance of NetRPC systems of distributed training and distributed agreement. We also observe that NetRPC can achieve even better training throughput than ADP and brings about 12% higher throughput than pFoxes. And we run NetRPC applications of different types and different numbers on the same system. And we can observe that NetRPC can support all these different types of INC applications with little performance loss. And finally, we measure the NetRPC system performance under different packet loss rates compared with prior arts. And in all these different types of experiments, we can find that NetRPC shows the least performance degradation under different packet loss rates. compared with prior distributed training tasks, systems. And in conclusion, to our knowledge, NetRPC is the first framework that integrates INC into the RPC program model. And NetRPC overcomes the program difficulty of INC with little performance loss. And in the future work, we plan to explore the scheduling policies of NetRPC and try to scale it to more complex topologies. That's all. Thanks.